Everyone, welcome to this video lecture on a random variable. In this video lecture, we are going to present or to discuss the essence or understanding of a random variable and why it is being considered as a foundation for uncertainty, something system or that involves uncertainty, such as different mathematical models, AI models, simulation models, and any other phenomena that involves with uncertainty. Random variable is the foundation. It is a key concept that has to be understood by the one who interested to analyze critically the system under uncertainty. So, before formally defining this random variable, it is good to understand the intuitive, the example, and the idea or the essence behind this random variable. So, as its name indicates, it is about randomness. So, what we mean by exactly, let's consider an intuitive or illustrative example. For example, in the real world, uncertainty is inevitable, meaning that whether a self-driving car is estimating the probability of a pedestrian crossing or a software reliability model is predicting system failures, uncertainty must be quantified. Because something that is not measured cannot be studied its impact. This is the reason where random variables come in. That means it serves as a mathematical bridge between randomness in the real world and the numerical competitions that software and AI systems that rely on. Actually, this concept of random variable is not limited to the software and AI systems rely on. That's the reason why we emphasize it is just the intention of our course and the scope that we want to address. However, this random variable is as if is just a foundation and a fundamental concept to be understood or that has to be understood for uncertainty, any system that involves with uncertainty. So with modeling, with simulation, with probability theory, and with prediction or forecasting events. So that is what it means. The intuitive understanding of random variable is so crucial, especially in today's AI model, where it is a fundamental concept or essence of uh, see, the underlying system is stochastic random process, so it is quite obvious to understand the idea of random variable. Having said that, then what this video covers, it starts with the formal definition or the mathematical definition of what is a random variable. Let's see the definition. For instance, a random variable is a numerical representation of uncertainty. What we mean by that, it is a function that maps every possible outcome of a random experiment to a real number. So in this case, there are key points that has to be addressed. It is a function and it is mapping of every possible outcome of a random experiment. So the experiment must be a random, and then there has to be an assigned uh, real value to that specific uh, possible outcome of the random experiment. So let's see uh, example. For instance, this is the example. So let's consider here, for instance, the example here, it says network transmission success. So that means for every outcome S, element of S, that is a capital S, then the random variable assigns a specific real number X of S. What we mean by that? Let's see that one clearly. So, for instance, let's consider an experiment. So there is an experiment E, then there is an associated sample space of this random experiment, and then there is an outcome or S, which is an element of this uh, total sample space. So let's consider an example. For example, consider a computer network where a client sends three data packets to a server, and each packet transmission can either succeed or failure due to the network congestion or signal loss. So that means That means the computer network. So that computer network, let's say there is a client and there is a server. So if this client sends 3 packets to the server, and then what could be the outcome of this network transmission? Because all the outcomes could not be success, or all the outcomes could not be fail, or either of the outcomes could be fail or success due to the signal loss in in between the transmission of the network. So in this case, consider this sample space, which is omega, and then the possible outcomes of this 3 packet transmission, where their outcomes could be FFF, FSF, FSF, or SSF, FSS, and so forth, and then SSS. So that means we have these possible outcomes, and then we have a real valid number system R, and then we have a random variable which is considered as x omega, then that maps every possible outcomes to a possible real number system, says that 0, 1, 2, 3, for instance. So if omega reads the specific element of S for the capital sample space, then if it reads the number of failure, then 0, meaning that no failure, for example, if it is all S. And then if it is the omega reads, this x random variable reads the number of failure, then this is 3. And then the others could be mapped to 1, and some of them also could map to 2, for instance, FFS. So what we mean by that? We are saying that the possible value of x omega is obviously, it could be either 0, 1, 2, or 3. So to make it briefly, a random variable x, which is considered to be a discrete random variable, we will come to that next, then should satisfy two assumptions. So the probability of x should be non-negative, and then the sum of the probability or total probability should give the sum of all probability over all possible values, n should give 1. So this is what it means, what a random variable is in brief. So you can see here, it is obviously the random sample for the random experiment for this computer network application, where a client sends 3 data packets to a server, could be either 0 or 1 or 2, 3. So what it means by 0 means all packets fail to send, 1 means 1 successful transmission, 2 means 2 successful transmissions, 3 all packets sent successfully, as I have said it. The other example, illustrative example, to understand the concept of random variable, take testing case execution. For example, a software engineer executes 3 automated test cases for a new application feature. Each test can either pass or fail. Similarly, the sample space as pass or fail can have 8 different outcomes. And similarly, the random variable x omega, which where omega is the subset of the larger omega, which is either 0, 1, 2, or 3. And we should also understand the fact that the probability of that random variable should be non-negative, and the sum or the totality of that probability should be 1. So in general, the outcome could be success or failure or whatever, like computer system, but in binary, where just computers understand a binary number system. So in that case, if you see the alphabets or the keyboards that we use for using alphabets, they could be represented as 2 binary digits, either 0 or 1, or on or off for any electric bulb, switch or off. So that random variable is either 1 if the outcome is the expected one, that is the success, and then if x equals 2, otherwise 0 if the outcome is fail. So this is the reason why we need to change the value or the outcome into a numeric one in order to model that concept of randomness, because computers at the end of the day understands the numeric representation. So types of random variable are two mainly. There are two types of random variable. For example, discrete random variable. What we mean by that, a discrete random variable takes on countable value, often representing events that can be uh, enumerated. For instance, the number of login attempts in a security system, that is a discrete. That means that you can't assume an infinite number of login attempts in a security system. That is, just they are countable and fixed in a certain interval. The number of times an API request fails within an hour. That means the number of times an API request. So the number of requests. So in this case, it is a discrete random value because it assumes a countable value in a given range. Then the other example, just the number of spam messages detected by an AI classifier. Again, this is a discrete random variable where mathematically they should satisfy probability of x greater than or equal to 0, that is a non-negative property, and the total or the sum of the probability under that experiment should sum up to 1. Example, let's take software reliability. Suppose the number of software crashes per day follows this distribution. Let's say the crash is a random variable where its possible value is 0, 1, 2, 3, and then the probability of each crashes, for example, for 0, 0.5, for 1, this is given as it is. So the probability x equals to 2, where x is the crash, then it is 0.15, means there is a 15% chance that the software will crash twice in a day. So this will give you an insight what it means reliability to the software engineer. So based on this quantification or numeric value, then the service level agreement could be adjusted or revised or even rejected based on this quantification. That is now the importance of studying the random variable. I think by now it is so clear. So let's come to the other form of type of random variable, which is continuous random variable. A continuous random variable can take on an infinite many values within a range, typically corresponding, representing measured quantities such as time, temperature, or latency. In this case, for instance, take CPU utilization percentage over time. It is obviously you can assume an infinite number of percentage or utilization rate over time. Response time, for example, for server response time, it is again can be modeled using continuous random variable. So in this case, there are two properties which makes it different uh, from from the continuous one. So this means, let's say x is a continuous random variable, so it should satisfy two properties. The first one is the integration of that over a specific value of x, f of x, where f of x is a PDF probability density function, then it should be non-negative. And the second one, it should be the integration of uh, the integration of this should be 1, and then the f of x by itself should be greater than or equals to 0. That means the non-negative property. The non-negative property should be satisfied. So in this case, what it says that for a continuous random variable, of course, probability of x at at a constant value is 0. There is no doubt about it. And then in a given range, it should be probability of a less than x less than b for two different values. Then the random variable between two values, then can be integrated in the form of a to b f of x by dx. So this is the mathematical or formal definition of a continuous random variable. So what is a real life applications in software engineering? Example 1, server response time. So what it means by server response time, in this case, let's take an example where the server response time, a client can send a request, as I said, at the server, and then we can measure the server response time starting from T0 up to TTI or ti minus 1 up to ti. So in this case, what is the variability among different requests from the client for the response time, for the server response time? So what type of distribution it follow? So after we do some simulation or modeling, we come to the conclusion that that random variable, for instance, follows a normal distribution with mean mu and with variability of sigma square. So in this case, for instance, if x is greater than 150 means milliseconds, that's the server response time. The empirical study shows that that response server time follows normal distribution. That is a detailed mathematical probability theory concept. It requires to understand this. Now, for this scenario, let's consider two examples. Probability of x greater than 150 and probability of less than x greater than x less than 150. So what it means that this is also all about quantifying things as a service level agreement. For instance, the probability of x greater than 150, that is the first case. The second case is now just any value between 100 less than x less than 130, for instance. So if x is normally distributed with parameter mu and sigma square, then by default f of x is, it follows a certain distribution where this is half x minus mu over sigma square, where x is under this range and then sigma is greater than or equals to 0. Maybe variance could be 0 for constant value at some point. Okay, so so that means you can compute the probability of this. So to make it the idea very clear, that means let's say this probability of x greater than 0 is just uh, greater than 150 means the probability of the server response time to be greater than 150 millisecond is 0.3, and the probability of x between this range 100 up to x less than 130 is just like 0.2. So which software engineer product or app millisecond in terms of the server response time. That's one metric, by the way, for software reliability. That's the server response time. So which one model or which one metric is preferable by the end of the day by the client? The client do not care about the details. The client will see the final metric. So which one, the lesser the server response time is, the more the better in terms of service response time. So in this case, the probability of lying between 100 and 130, automatically it is less than 150, and the probability of between this means it is 0.8, 0.2, which is lesser. That means higher amount is to be less than this, whereas this to be greater than 50, the chance is 0.3, and at the same time, it is greater than this margin. Even the maximum margin of this is less than this, or this one is greater than this. So the one that with lesser response, server response time will be the best one by the clients. So the other thing is software failure modeling. Let X represent the number of bugs, you see, detected per week. So the Poisson distribution is often used to model such function. By the way, it's good to understand what it means, the Poisson distribution. The Poisson distribution here is that a Poisson distribution is, let's say X follows a Poisson distribution with parameter lambda, where the number of bugs is supposed to be how many number of bugs uh, could be involved or could be obtained per week. So the lesser the number of bugs, then it follows the Poisson distribution. That is the assumption, the underlying assumption of Poisson distribution. So that the probability of x equals to x e minus lambda, lambda the power of x over the probability e minus lambda, lambda the power of k, okay, power of k, then k factorial, where k could be finite numbers up to n for that matter. So in this case, what we mean by exactly, for example, if you have lambda equals to 3 means average number of bugs a programmer or a software engineer or whatever software tester could do per week, its end product, that is the software or the software solution or whatever, any application. Therefore, if the probability of x equals to 0 means that if you put this value, obviously we are saying that 0.049 means almost 4.98, 0.8. So that means the probability of x equals to 3, we are saying that that lambda is 3, and then 3 is the power of 0, and then 0 factorial is 0, is 1, so that is 0.498. So this implies 4.98 are the number of bugs that could be done per week. This isn't it too huge? It is too huge. So this shows that the software solution has to be revisited and reviewed. Maybe it is requirement, maybe it's other issues that has to be checked at different phases, starting from the design and requirement, coding, implementation, testing, verification, validation, and implementation. These all things could be it's just a reminder to be checked, because the bugs per week are too huge. 5% almost nearly per per week is too much, because the requirement for software is reliability, number one. So that means there is a 4.98% chance that no bugs will be found in a given week, a valuable insight for reliability analysis. So that means about 5% chance that no bugs will be found in a given week. So that means it is less. It's just only 5% no bugs will be found in a given week. So this is what the random variable concept helps us again quantifying the the impact. That's what exactly it is doing. Another thing is random variable in AI, in artificial intelligence. That's the most important is the Bayesian network. So in case of in probabilistic graphical models, this concept is, by the way, the probability theory and the graph mathematical model is integrated to address another phenomena, which we call them the uh, relationship between nodes. So each node represents a random variable such as sensor reading, weather condition, or user behavior, depending on among dependencies among them define how knowledge and uncertainty propagates through the model. Obviously, for instance, uh, you can consider this example in case of the probabilistic graphical model. For instance, here it says, let's say time time spent on coding to uh, uh, efficiency efficiency of a code. So that means the amount of time it is spent for a programmer to do a given task, does it affect its efficiency? So in this case, if there is a relationship, or if there is a relationship from time spent to efficiency in one side, then this kind of causal inference or causal relationship could be is just is being is being uh, uh, is being happening. That means causal relationship is being formulated. So in such scenario again, this random variable is important to understand for Bayesian network. So probability of rain, for instance, given cloudy equals 0.8. That means probability of time spent uh, is, so what it has to be, which one is dependent on which. So the time spent, the efficiency, see? So the efficiency given time is certain value, because the probability of the efficiency on the code depends on the amount of time, the time of that means attention, the type of experiment, the type of simulation, the type of code, the type of framework, the type of application by itself, and the type of experience even could be an impact on efficiency. So this is just one variable. So that's why that variable under study could also affect the outcome, and another variable also could affect. That is why at least if one variable is uh, random, then the entire process that generates that experiment is assumed to be random. So another issue is neural network dropout. This is very clear in Bernoulli distribution, where every trial has its own outcome, and then every outcome of that trial is assumed to be independent. And then in this case, again, the outcome is assumed to be binary. That means where Z1 means the neuron is active. By the way, this is true also in artificial neural network. Where the neural is active, then it will be 1. Where it is otherwise 0, that means it dropped. That means the neuron is no longer able to learn from the set of neurons. Then this stochastic behavior prevents overfitting by simulating random subnetworks. Another is reinforcement learning. Then in this case, the reinforcement learning, there are three main variables: learning, the reward, in reinforcement learning, the reward, the state transition, and action outcomes. So that means the agent estimates the expected reward, expected of E, RT, ST, given ST, 8, meaning that given that these two, the state and the action, will have a dependence on R. So that is the reason why this is also considered as one random process in its nature. So this probabilistic reasoning allows agents to make robust decisions under uncertainty. So key properties of random variable, obviously, the this property is quite interesting and important to understand the concept behind. So the properties is one, the expected of this, the random variable is, it can be defined as expected of probability of x for xi over all possible value of x. This is for discrete. And for continuous, it is assumed to be expected of x. This is the integral of x, f of x by dx over all possible value of x. So then the non-negativity is again there. So the variance is again also just can be defined as expected of x minus expected of x the whole square. So by after many steps, by using the a minus b other property, mathematical property, finally as a competing formula for variance of a random variable can be given as this one, expected of x the whole square. So this is a competing formula for variance of a random variable. So to summarize these two concepts, possible value for discrete random variable more or less countable, but it does not mean that it does not assume negative decimal values. It could assume some decimal values, but there has to be a regular interruption or just a regular gap between this, unlike in continuous where it assumes an infinite, uncountable infinite possible value. Then number of failed logins, server response time are respectively the examples for discrete random variable and continuous random variable. Then possibility measure probability most function, that's probability measure. This is defined as PMF, and then that has also PDF, that is a probability density function. And then computation of probability, just you can compute the probability of x equals to x for discrete, and that is the summation. And here continuous, you can use the integral in order to see the uncertainty over all possible values of a given interval. So to wind up our concept or lecture, why random variables matter to study. Obviously, in software engineering and AI, and in any system where uncertainty involves, and of course, in real life, uncertainty is inevitable, as I have said at the beginning of the starting of the video. So they quantify uncertainty in real world data. That's number one. They enable predictive modeling and decision making. They form the foundation of probabilistic reasoning and learning. So the takeaway is nothing else. It's just we want to quantify and we want to measure the impact. Something that does not measured could not be studied its impact. That is the key point of why random variables are so important to understand them. So, as a conclusion, random variables are not just mathematical abstractions, they are the language of intelligent systems. They allow machines to make sense of randomness, model complex realities, and make data driven decisions. So, the today's fourth science of AI models, the chat GPT, and all machine learning, the prediction, the data science, the probability theory, they are underlining fundamental concept being founded on uncertainty, so that in order to study that uncertainty, its impact, then random variable is the key concept to be understood or to be studied. Understanding random variables is understanding how intelligent systems learn, adapt, and reason in uncertain world. And thank you very much.